in this presentation, I will talk about how we use the AI in a commercial context in order to try to detect the parking spots on a large and dense urban area. So in this presentation, I will go through the detail of the mandate that we conducted. So I will go, sorry, I have to look there, sorry. So yeah, starting with a bit of context, because the context of this mandate was a bit particular. I will then dive a little bit more in the domain expert problem that we try to solve during this mandate. I will talk a bit about the technology that we use, so how we used Python to try to tackle this problem and the domain experts that were facing us. I will speak about the data that we used to train the model, because it was, of course, there was an AI model within this project. I will talk about the result that we obtained using this model, and I will end up this talk with a few words on the geomatic part of this project, because the geomatic part followed the AI part. So just first of all, a few words of the company in which I work for. So we are a small GIS company that we are based in Geneva. So we have roughly 30 people that are working in the company. So we have mainly two teams working in the company. So we have a development team, so teams of developers that are developing specific application related to geography and GIS, and we have also a geomatic teams that take care of more geomatic services. So there is also an AI team that is starting to shape up. Hopefully it will lead to a third team in the company. So of course, we are a small company, but we are managing to invest a small amount of money into research and development, and that's why we decided to go through this mandate that I will give you more in detail. So first of all, of course, as we are a private company, we have to make money for sure. So we conducted this project as a usual GIS mandate. So it was typically an offer that we answered to a call for offer in order to set up this project, and with a little bit of R&D on our side. So we were in the case where we had a customer in front of us that was expecting results from us. So it was quite a challenging environment to do AI. So in our case, the client was the urbanist department of the city of Rennes in France, so a big city. And the need they had there was to try to compute an inventory of the parking spot. And I will detail how we have done that. So we proposed an AI approach to try to tackle this problem. And it was quite a challenging mandate, because it was really outside of any research environment. So we had a client that was expecting results from us. So let's dive more into the domain expert problem. So in the city of Rennes, they have this problem that is quite common in geography, and moreover in GeoAI, is this need to be able to compute an inventory, and here an inventory of the public parking spots. So this necessity comes from the political side. So the political side will give some mission to the urbanist department. And one of these missions is to be able to compute on a regular basis an inventory of the parking spots all over the urban area. So there are different political reasons behind that. So you have, of course, basic understanding of the state of the parking spot to make statistics to understand the offer in front of the demand. You have also a question about helping the urban management and planning, so it's important for them to have this type of inventory. And it's also helping the ecological transition, because they are questioning more and more the usage of car in this city. So before we came with our solution using AI, the only solution for the client was to do it manually. So to hire basically human agents to work on aerial images to spot manually each and every parking spot on the whole territory of the city. And it's, of course, something that is very time-consuming. It's error-prone, because it's very difficult to not miss anything while doing this manual process, and it's something that is costly. And moreover, it is quite not a good solution, because if you have to restart the whole process with a new set of aerial images, you cannot really leverage all the experience that you had on the previous manual annotation. So that's the reason why we decided to propose an AI approach. So it was a bit of a particular collaboration. So what we proposed to the client was to offer him a teaching on how to use AI and to bring all the tools required for him to use AI to, by himself, being able to compute this inventory and maybe to carry on other objects on the territory. So something that was important as a commercial collaboration is that to make sure that the client understood what AI was about. So maybe you already saw that in your different domain, that sometimes people think that AI is kind of magic. So you can snap your finger and AI will solve everything, but that's important to explain to a client what AI is about, what is the AI process, and what is the limitation of AI, and what is the cost of using AI. So we also emphasize that AI has to be seen as a long-term investment, especially in such a department. And we placed our offer during this call for offer, and we win the offer. So we were selected by the client, and that's how this project started there. So let's dive a bit into the technology and the Python tools that we developed in order to bring the client to be able to compute this inventory. So basically, this is quite a simple application of AI and GeoAI for in front of the client needs. So basically, it's just a question of leveraging aerial images in order to be able to extract the parking spot from the aerial images. So we had the chance with the city of Rennes to have a good quality aerial images. So it was a 10 centimeter per pixel images that we were able to use to do this task of extraction. So it was quite a nice data to work with because it was sufficiently precise in order to spot and see clearly the parking spot. And it followed that the client needs can be to some degrees reduced to a simple object detection problem using AI, and more specifically, I will talk this more in detail later on, more specifically an instant segmentation problem. So in the beginning, the client has no annotation whatsoever. So no ID, where are the parking spots located on this territory. So we had no geographical layer on which we can base our, we can use to try to build a training corpus. So the annotation was on our side, and more specifically, it was a complicated case because the client was not interested in the parking area, but the individual parking spot. So to be able to count how many cars you can actually park on the whole territory of the city of Rennes. And as you can see on these images, on this image, is that on the ground, the way the parking spots are labeled, are marked, are very often continuous. So you don't have a separation, a clear separation between the individual spots. So it's quite complicated to detect the individual spot in this situation using AI tools to achieve that. So we then proposed the following strategy. So the strategy that we proposed was to, first of all, use AI to detect the parking area as a whole object, regardless of how many parking spots there was in each parking area. So that was the first phase that we decided to do. And then to infer the position and the count of the individual parking spots using templates. So a standardized size of a typical individual parking spot in order to be able to deduce the amount and the rough position of each individual parking spot in the detected parking area. So that's the reason why we had to choose instant segmentation instead of object detection, because instant segmentation would bring you the geometry of the parking area that we rely on in order to be able to infer the individual location of the parking spot. So in this project, we of course proposed the client to go with the YOLO model because it's the most suitable for this type of task. It's very impressive in terms of performances. So it's a model that is able to produce mask, and you can very easily extract geometry from mask in order to get the geometry that you need to detect this object. So we had to fine-tune the model, of course, because this foundation model does not know how to detect the object that interested us in the first place. So we had to perform this fine-tuning. And we had also to develop on our side a whole framework being able to bring geographical data into YOLOV and then to bring them back into geographical coordinate, because YOLOV does not come with the support of geographical coordinates straight away. So that's what we developed for the client, for him to be able to ingest all its data into the YOLOV to perform the actual training of the fine-tuning of the model. So let's dive a bit more into the way we prepare the data, how we created the corpus to fine-tune the model. So here, as I mentioned, there was no annotation whatsoever. So we had no layer on which we can rely on in order to build a corpus. So we had to do the annotation work by ourselves with the supervision of the domain expert of the city, of course. So we developed different Python tools in order to be able to build grids on the territory. So these grids that were computed with Python script were in their characteristics synchronized with the images. This is done in order to avoid to have to resample images if you want to create subsequent grids in order to try many type of subgrid to actually perform the training. So we started with this base grid, and this base grid was really used to define the area on which we will perform the manual annotation of the images. So you can see on this image the green cells are the cells that we use to make this manual annotation, so to really spot each and every ranking area that were present on the images, to build a ground truth that will then be used as a base to build a corpus to fine-tune the model. So that's based on this grid that we deduced different corpuses. So corpuses are really the data that will really be fed into the model. So we didn't use the base grid, the annotation grid, because the cells were way too big to be fed into an AI model to fine-tune it. So we had to define subgrids more suited to train the model. So we again developed some tools here to take care of this aspect. So to be able to deduce subtiles SimSim from the main tiles that we use to annotate the image in order to be able to feed the model, to fine-tune the model. So in this operation, we have to take into account that when you train a model, you have to take into account the hyperparameters. So you have a lot of hyperparameters that are around the model, and you have to be very careful on this aspect, because this parameter can influence a lot on the quality and the performance of the model that you will obtain at the end of the training process. So we had to consider here two very important hyperparameters, which were the geographical size of the tile that were truly sent to the model for training, and the resolution, because the resolution is important because you have to be able to see all the details of the object that you are trying to detect, but you want to avoid to have too large images because it will be complicated to feed them into the GPU. So you have to find some kind of a balance between both, a good resolution, but tiles that are a reasonable size, and you want also to try to limit the amount of tiles that you will obtain with your corpus, because dealing with a lot of tiles can be quite tricky, especially in a collaboration with a client like that. So we had to do this balance. So we developed scripts able to deduce these subcorpuses. So we do it in a way that we can tweak the geographical size, the resolution of the images, in order to be able to test many different configurations, in order to see which were the hyperparameters that were performing the best for the task that we try to achieve. So, of course, as always, so if you have done deep learning, you know that very well. So in deep learning, when you have a corpus of data that you will use to train or to fine-tune a model, what you have to do is to separate the data into three categories. So you have a first category that is called the training set. So the training set is really what you will show to the model. So it's the data on which the model will actually learn to detect what is interesting you. Aside of the training set, you have the validation set. A validation set is very important because it's a set that is not formally used during the training, so it's not seen by the model. The model does not see the validation data, but we still compute the metrics, so the performances of the model along its training, to keep track of what happens on tiles that are not seen during the training. So it's important to consider validation set in order to avoid overfitting, and we will have an example just after. And the last group that you want to define, it's not an obligation to have this third group, but it's a good practice to have it. So the test group is reserved set of tiles that you will never use during the training of the model, nor to track the metric during the training or the fine-tuning of the model. So it's something that is completely reserved at the end of the training for you to be able to test the true performances of the model on data that he never saw during the training. So untouched data that was not used during the training. So in our case, we end up with a training set with roughly 14,000 tiles containing roughly 4,500 annotation, and the validation and test set were just made of 1,200 tiles. So quite large data set for quite a small region, but we end up with so many tiles because we defined a large overlap between the tiles, because it helped quite a lot the model to learn the object that we try to detect. So with the chosen hyperparameter that were the best performing, we were able to launch the training, so the formal training, so to use the training data that we were prepared to really fine-tune the model. So we worked entirely on the client side. So the client provided us a workstation. So it was a workstation that you can find in many desks. So it was quite a reasonable machine with a consumer-grade GPU, so a single consumer-grade GPU. So it was quite easy for the client to be able to perform this fine-tuning, because it didn't requested a large amount of computation power. So we made several training sessions in order to be sure that all the training sessions were consistent with each other. So it lasted between 12 hours and 1 day of raw computing to fine-tune the model. And you can see on this plot here the two curves. So you have the training curve and the validation curve. And we can see how this validation curve will go up at a certain degree. And that's why it's so important to have this validation curve. It's to be able to detect when the model will stop to learn. So it will become less performant. So in our case, in almost all of our training session, the optimal checkpoint were obtained after around 30 epochs. So an epoch is defined as one epoch correspond to the model to have seen 1 times the entire corpus. So 30 times mean that the model has to see the corpus 30 times in order to reach its best performances. So with this model trained, so we have now at this stage a model that is able to detect the object of interest, hopefully. And now what we have to do is to check to which degree this model is really able to achieve this task and with which performances. So it was really important for our client to be able to quantify this data, for them to understand how AI can really truly solve their problem. So, of course, the evaluation was done on the third set of third part of the corpus, so the test set that is reserved, so not used during the training. So it's something that we only keep to evaluate the model. So what we do in this stage, it's quite simple. So we take all the tiles that are in the test set, and we submit the tiles to the model for it to make prediction on these tiles. And because it's part of the test set, it's part of the ground truth. So we know exactly the situation of the parking spot on this tile of the test set. And the evaluation consists simply of comparing the both. So you compare the prediction with the ground truth, the real situation, in order to be able to define, to quantify how the model is performing in front of the task he has to solve. So here, the only technical graphic of this presentation. So that's the result that we obtained. So we obtained quite good result for the complexity and the diversity of the parking spot. So we had F1 score that peaked at 85, which is quite good for the optimal threshold. So for if you don't know, the F1 score is just a combination of the precision and the recall. So it's just these two measures that are put together, and the F1 score can only be high if both are high. So roughly said, precision will tell you about the quality of the inventory, when the recall will tell you roughly about its completeness. So having both together tells you if you have a good model and how it can really perform on this task. So it was interesting because the client was satisfied with this result he got from AI. So for him, 85 as a F1 score was sufficient to demonstrate that AI is an interesting technology to tackle this domain expert problem. So with this model in hand, we were able to launch the inference, so the detection, so the computation of the inventory over the whole area. So we just run the model over the entire set of images covering the entire area, and we were so the model just made prediction on all the tiles, and we just received this prediction. And with the development that we put around YOLOV, we were just able to get a standard geographical layer. So what you are seeing here, and what comes out of the AI is just a regular geographical layer. So you can straight up open it in QGIS or ArcGIS to check its content. So this one contains, so the layer that we computed contains roughly 24,000 prediction. So this inventory was computed in a few hours, so it was extremely quick. So the model that we used for this project was really efficient. So in a few hours, you can compute a relevant inventory of the parking spots, detecting roughly 25,000 prediction in a few hours on a small workstation without needing huge computation power. Just to so this conclude the AI phase. Just to say that what you are seeing here is really the raw result going out of AI, so no filtering whatsoever. So in order for the client to be able to use this result, furthermore, work has to be done on it in order to filter a bit things. So in this case, that's the AI team of my company that took custody of this part. So it was a geomatic part. It was not, so it was done in FME. So I won't be too much cheating here, but just give you only a few words about what happened after the AI phase. So basically, when you have an AI layer, you still have mistakes. So you have false positive that remains. Some of them are easy to spot. So some false positive can be really small detection, or really can be considered as noise that are easy to spot and that are easy to get rid of with simple geometric consideration. And moreover, the client provided us with complementary geographical data for us to furthermore filter the data. And also a complicated question was how to detect if a parking area was on the public domain or not. So the client provided us with land register and administrative data for us to be able to filter both the private and the public parking spot in order for us to end up with a relevant geographical layer. And at the end, of course, because the client was interested in individual parking spot, we had to make this inference of individual parking spot based on the geometry of the detected parking area. So we used a geometric criterion in order to be able to translate this geometry in a set of points, each point representing an individual parking spot. And also there was a whole question about domain expert data that was added to this point as an attribute feature in order to complete the dataset. So this punctual layer that you are seeing on screen here was the inventory that was obtained and delivered to the client for him to understand the offer of parking spot on its territory. So this concludes this presentation. So just last word to close this presentation. So quite a challenging project, an application of AI that was mixing business, AI, Python, domain expert, geography. It was quite demanding. The client was only interested in the result, not really on how the results were obtained. But it was interesting because it demonstrated that AI can really be sold. You can build services around AI in a small company and conduct this commercial collaboration in a successful way. So that's it for me. Thank you for your attention. If you have questions.
Thank you, Nils. Are there any questions? Okay, I see some hands up.
Thank you for the talk. I was wondering, did you look at, because like parking spaces can be filled or not, did you also consider or do something with that fact in choosing training data, maybe looking at, okay.
That's a very good question. No, we completely ignore this part of the problem, which of course makes sense. The problem is that if you detect cars, you have the huge risk of having a model that will start to detect cars all over the place, because roads are shaped in a very similar way as the parking spots, because you have marks on the ground, you have cars that appear to be static on the images. So it's quite that was a choice we had to make. We went to something simple because we didn't have much time, so it was not a research project, so we have to make quite rough choices, but it's a good question. We ask ourselves this question. We choose not to separate both. We decided to go single shot and see what happens. And it worked quite well.
Thank you.
Hi, thanks. So as I saw your validation and training losses, you stopped at the 30th epoch because it started to overfit fairly, but also that gap shows that it's overfitting. So I suppose that you still had a lot of work to clean false positives, as you showed. You didn't want to go deep into FMA, but FMA is just a tool. So any ideas? Because I was doing something similar, and the overfitting was quite logical because the parking spots were on roundabouts, big, would have some marks and stuff like that. So how could you clean that from your perspective? Like any ideas?
So yeah, we didn't have much time to do that because we were quite on a tight budget and schedule. So we only consider easy filterings to some extent. So there were a lot of situations. So you have simple situation where you have obviously wrong false positive that are easy to get rid of, but you have many situations where the roads and the parking spot are very alike, and you have the model just is confused between both, but we didn't have the time to dive into solution that could be applied there. So the client was only interested in answering the question, does AI make sense for them to bring into their everyday work? So we got to the most simple thing. So we didn't really have the time. So we use basically easy geometry filtering, and then we use complementary data to furthermore filter and try to do what can be done with this type of layer, but not much than that.
So thank you for a very interesting topic. Just one question about the data. So did you consider to use street level data for example, I know usually parking spots came together with trees, so from above it's very difficult
Yes.
to detect those spots. So did you consider to use other data, for example, street view?
Yes, Street View, we looked at Street View in order to be able to look at different things. So on Street View, we tried first to get annotation from Street View because we were lacking annotation in the beginning of the project. So we tried to see if this information was in OpenStreetMap, but it was not the case. So only the large parking were marked on OpenStreetMap. We also try to see if we can locate a specific object like bike lane, because bike lane was a case of false positive that was recurrent in our results. So we try to see if bike lane could be extracted from OpenStreetMap in order to be able to get rid of them, to detect the false positive this way. But the data was not sufficiently filled on the city we were working with, but not much than that. Again, it was on the tight timing, so again we went to the simple stuff in order just to prove that AI makes sense, but not much. There is, of course, from all your question, you are totally right. There is a lot of work to do more on this type of detection, but we didn't have the time to do that. But we looked at OpenStreetMap, but not much than that.
One more question from me. Did you use any data augmentation techniques during the training?
Sorry?
Did you use any data augmentation techniques during the training?
Yes, we used the standard word provided by YOLO, not much than that. So one thing that we worked more extensively was the overlap, because the overlapping of the tiles that we used tends to greatly increase the performances of the model. So that's the only augmentation, but I'm not sure if it's a formal augmentation, just to speak about overlap. So just the basic one.
Okay, are there any questions? We have time for one question. Okay.
If you can you give some details on the technology stack that you used throughout the data preparation training?
Oh yes, Python extensively, because it's very easy to interface it with YOLO. And what we used a lot was, of course, GeoPanda, because GeoPanda is the best things to use to do geography. It's efficient, fast, and you can do a lot of stuff. So that was the main two technology that we used. It was GeoPanda to deal with all these geographical aspects. So to bring all the data in the model and then to get them back as a geographical layer. So it was mainly GeoPanda and YOLO, of course, on the side of the client.
Okay, thank you, Nils, for your talk.